Hello, good morning. I am Danilo Cole from ENGINESoft. Thanks to all those attending this webinar on industrial application obtained by mass reduction and performances implementation for powerful optimization tools. I'm happy to introduce you Juan Pablo Leiva, who is currently the President and the Chief Operating Officer of Van der Platz Research and Development. He is one of the main developers of the GENESIS structural optimization program with more than 20 years of experience. In this webinar, he is going to introduce first the optimization tool, GSAM and GENESIS, and he will show some industrial examples and more in detail the design of a powertrain component using topology optimization. I let Juan Pablo the role of presenter.
Thank you very much, and thank you everybody for the attending this meeting. Thank you, Danilo, for the introduction. As Danilo mentioned, my name is Juan Pablo Leiva, and I work for Van der Platz R&D. And today I will talk about industrial application using GSAM, which is a tool that couples optimization, GENESIS, with ANSYS in the ANSYS environment. The outline of my presentation is here. I basically give you a very brief introduction of the company I work for. I will talk mostly about GENESIS, GTAM, and GSAM capabilities. I will briefly describe optimization types. I will give you examples, and I will give a more extended example used in the industry, and I will finish with a summary. My company was founded in 1984 by Dr. Gary van der Plaat, which is very well known in the optimization community. He founded after working some years in NASA and in academia, and he found the need of creating optimizers, and he started commercialize it when the company started. We have multiple tools in the area of general optimization and in structural analysis and optimization. Our main software in the structural analysis optimization was GENESIS, and we were invited by ANSYS to couple that with their ANSYS workbench, and we created two new products called GTAM and GSAM, and these two new products I will describe in this presentation with more detail than the rest. I would like to mention that we are partnered with ENGINESoft for some years now, and in 2016 they became a reseller for us, and they commercialized the GENESIS, GTAM, GSAM. So if you're interested in this tool, ENGINESoft is a good place for you to, to be and attending this webinar. Let me start saying what GTAM and GSAM are. GSAM and GTAM are acronyms for GENESIS Topology for ANSYS Mechanical and GENESIS Structure Optimization for ANSYS Mechanical. GTAM is focused just in topology, whereas GSAM focuses in all GENESIS capability, including topology. Basically, GSAM is a superset of GTAM. Before talking too much about the software, I would like to know why people use this kind of software. These are optimization software, so the goal is to obtain a structure that can be lighter than the original structure, that can be cheaper to manufacture. The people who use this kind of tool to improve performance, sometimes to satisfy design requirements, sometimes all of the above. People like to use our tool because also reduce the design cycle time. As I'll show you later, GENESIS is very efficient, so it can converge in very small number of design iterations. People like to use GTAM, GSAM because it's easy to use. If you are in the ANSYS environment, you don't have to get out to use the tool, and that's why it's easy to use. But ultimately, people like to use this kind of tool to innovate. People want to have final design that are better than their competitor, better than the previous year design. So this is the motivation to use this tool. We've been working with these tools, GTAM, GSAM, since 2013, when ANSYS invited us to add topology to the environment. We released the first version in 2014 of GTAM, And we follow up with a version for GSAM in which we added, beside the topology, the shape sizing, etc. So we have two flavors for the interface, again, GTAM and GSAM. If you're familiar with the ANSYS environment, you will notice that you don't have to get out and you will use what you're familiar with. For example, you will use the workbench to create your analysis. You will use your ANSYS Mechanical to do the pre-processing, meaning creating mesh, load, boundary condition. And what is important here in this presentation is that you can use our GTAM GSAM to define the optimization problem. Then you will run GENESIS in the background, and you will be able to do post-processing inside of ANSYS, and you will end up with a structure that is in STL format. So you can use, for example, the design modeler or space claim if you're an ANSYS user, or you can use any other tool that use STL. You can also see the visualize the optimized mesh, and you can run it for verification or for other usage. So this is the flowchart that, or flow of work that people will use to use this GTAM or GSAM. The analysis capability include a static, normal mode, many types of analysis, but also include many types of optimization. And you can do all them together, meaning you can use topology and size it at the same time that you're optimizing for a displacement, normal mode, or a backlink load. Many responses are available, and these responses, meaning the software is very powerful because you can satisfy most of your design requirement without needing to run validation later. You can just include them in the optimization. The type of optimization mostly refers to what are you allowing the optimizer to change for you. If you are doing topology optimization, like in the top left, you allow the optimization to delete element. Basically, you want to keep only the important element, so you get a lightweight structure. In topography, shape, and freeform, you allow the optimizer to move the grids in hope to have a better structure. Could be lighter, could be stiffer, etc. And finally, two types of optimization called sizing and topometry allows you to change the physical dimension of the structure. In sizing, in the middle example in the bottom, the colors represent thicknesses. Red means thicker, blue means thinner. And topometry is a special case of sizing, in which each element can be designed independently. So this type of optimization are available in the GSAM, GSAM only for topology. And here's a more detailed example for topology. As I mentioned before, in topology, we start with initial design. The optimizer will make holes, and you end up with a structure that certainly looks much lighter than the initial one. I'd like to show you a very interesting example. This is an old example. It's created by Pratt & Miller. They wanted to make a frame of support for a wing, and they used the topology optimization in GENESIS to solve this problem. And in the middle, you show the final answer. The mass reduction is estimated in 33 based on what Pratt & Miller thought that they will do it without optimization. And to prove that the structure is light, here's a picture showing that you can carry that structure with only a couple of fingers. This is at the Pratt & Miller place. Another industrial application of topology optimization is to use it to find the best locations to create a reef for reinforcement. This example is provided by Cummins, where they wanted to stiffen up the front cover of an engine. These are large engines. I'm not sure this one, if it belongs for a train or a big truck, but these normally are very large engines. Sometimes they can be tons. The way you input the data in the interface is quite easy. You just fill forms. In the top, you see the bar that ACT extension will provide you. And when you do topology optimization, you need to fill 3 forms, one for topology region, one for your objective, and one for constraint. So by filling forms, you will be able to access all the analysis results that you could use for optimization. For example, you want to minimize strain energy, you will just pick it from the list. And your goal could be minimize or maximize, and you can have multiple objectives. Similarly, for constraint, you will pick some responses and you will create multiple constraints. You will put lowers and upper bound, so your optimization will maintain certain values in check. So topology optimization is easy because you only need 3 forms. Another type of optimization that is easy to use is topography. And in topography, we'd like to move grids up and down to create automatically bits. And the optimizer will decide where the bit locations are best. This is a torsion plate, so the optimizer decides to make bits in 45 degrees. That makes sense. And to create this data, there is a very simple form that you just need to fill up, in which you specify minimum requirements like the maximum height of the bits, minimum the width of the bits, etc. You can also impose fabrication constraint like symmetry. By the way, in topology optimization, you can also impose fabrication constraint, which make the software very powerful because you ask the software to create a structure that you really want to build. Sometimes the topology result or the topography result are very organic, but if you prefer an answer that is less organic, you can impose that. Here's an example from Cummins again for topography optimization, in which we want to create bits to make the structure stiffer. The initial panel was flat and very flimsy, I should say, but after the bits were put, the structure became stiffer. I think in this case, they were increasing the natural frequency. If I remember, it was 20% gains. So topography in regional, like mentioned, is just about filling forms and it's easy to use. You can see the result in the ANSYS workbench. The sizing optimization is about to finding optimal thickness dimension. And with the ANSYS software interface, you can create the data for that by just, again, filling form. As you can see, the process is not that complicated. How this work? How can GENESIS solve these problems? Here's a flowchart of GENESIS, and the key is the approximate problem. What we do is create an approximate problem based on analysis and sensitivity result, and this approximate problem is optimized with the optimizers. This can take a lot of iteration, like 150, for example, but the key is that because this is an approximate problem and made by explicit approximations, you really don't need to do 150 analysis. Actually, you need to do maybe 10 or 100. So that's the secret to have an efficient optimization. This is based on ideas that Professor Lucien Smith and co-workers implemented or proposed it in the 70s. And Dr. Gary van der Plat improved it in the 80s by creating what is called second generation approximation. So GENESIS benefits for this, and you as a user will get an answer faster. You don't want to wait for a problem that takes 1 hour, 150 hours. You want to wait 10 or 15. So in a problem that takes 1 hour, if you run it overnight, next day you get an answer. So let me show you, talk about application in industry. Today, this software is used in many industries. There are many applications. You can do from small bracket to large component, like full car bodies. You can optimize for powertrain component, engine component, MRIs, you name it. There are many, many examples. We like to say if you can analyze it, you can optimize it. So it's a matter of defining the problem correctly. I'm going to focus in one example, which is a powertrain component. And I'd like to give you a background of this example. There is a project called ULTRAN, which stands for Ultra Lightweight Transmission and Driveline. This is a project done in the United Kingdom. It's part of the Innovate UK initiative, and is led by Jaguar Land Rover. This is a multi-year collaboration project that many companies or institutions participated, and one of them is GRM Consulting in UK. There are partners of V&D, so I had to disclose that, and they provide me the slide. They informed me that the challenge was that they needed to simultaneously optimize for stiffness, strength, and MVH, meaning the final answer had to be good for all these type of conditions. The case study is a real drive unit, and this unit has already fabricated and is being used for demonstrating the technology and for testing. Let me show you some slides about this process. You see three structures that represent the loading conditions. One is for stiffness, one is for strength, and the other picture is for NVH. We are going to do topology optimization, and we want the red part, which is the design domain, to be processed by the optimization process. The first type of requirement is to satisfy stiffness requirements. Basically, there are 4 mounts, and to satisfy the stiffness requirement, the structure is loaded under 12 different loading conditions. 3 of the mounts are fixed, and 1 of the mounted is apply a load. And what they want is to make sure that the deformation under the load is less than a certain target value. If the displacement are low, mean the structure is stiff. If the displacement are high, mean the structure is soft. So the optimization will have 12 constraints for stiffness. The next load cases is a dynamic load case or harmonic, in which there is a torque applied of every from 200 to 850 hertz. So it's a spectrum load, and it's 1 Newton per millimeter. And the idea is to measure the acceleration at certain control points, and the acceleration need to be limited, because if the acceleration is too high, the constraint or targets are not satisfied. There's only one load case for this, and it's a frequency response or harmonic response. The next load case represent abuse, forward abuse torque and reverse abuse torques. These represent loads that are transferred to the casing as a result of operations. These 2 load cases has to be constrained so that the stresses in the structure are not too high. In the baseline performance, the stresses were around 217 and 207, the maximum. So you can see there is multiple type of load cases, and the engineers develop multiple solutions. In this slide, I show you 2 of them. In the left, they fix the max. I think the max they picked was the one obtained for another optimization run, and they consider only stiffness. If they do that, they get a structure that is indeed stiff, but the problem is the stress is too high. So they run another case where you are minimizing mass, but you have now considered stiffness and stress. When they consider stiffness and stress, the stress went down from 622 megapascal to 274 megapascal. So in this case, the stress went almost half, and was achieved by creating different solution. If you look at the circles, the ribs in the left are different than the ribs on the right. It looked like the ribs in the right are a little bit more smooth and thicker. So this example, at the end, they were able to meet all the design requirements. They were able to reduce the designable mass by 32%. And the total mass, which represent not just the designable part, but the other component, I believe was reduced by 25%. In the bottom right, you see a picture of the final structure. And as mentioned early on, this has been manufactured and tested. I seen this part in the UK, and it's relatively small. But again, this is part of a big project to try to innovate in power train development. So this is a interesting example that I wanted to bring to you today. So with this, I like to say that I talk about the tools, GTAM, GSAM, that allows ANSYS user to access the GENESIS software. I like to mention that these tools are efficient. I mentioned to you a flowchart in which we solve an approximate problem allowing us to need less number of finite elements that other methods would require. So it's very efficient. And I like to say there are a large number of applications. Basically, with topology, you can make holes. With sizing, you can change dimension. With shape, topography, and freeform, you can move grids. So you can imagine that in a given structure, you have a lot of freedom to change. And most importantly, I like to mention that this is a tool that people can use for innovation. So with this, I'd like to finish my presentation and return my microphone to Danilo. And if you have questions, please let us know.